Okay, guys, can you see the screen?
Yes, sir.
Okay. So this is our common emitter amplifier, and we want to analyze this amplifier circuit to determine certain amplifier parameters. The amplifier parameters that we are mostly interested in are the voltage gain, current gain, the input and the output resistances. The voltage gain we can define like this. So that is our voltage gain. The current gain similarly will be the output current given by input current. The output current is the current that flows through the load. that is our I naught. Input current that is supplied by the source and goes into the input of the amplifier. So that is our input current. So that is our coupling capacitor. This is CC2. This is CC1. The input resistance is the resistance looking into the amplifier at the input side. So that is the resistance seen by the signal source. Output resistance is the resistance looking from the output side, and that is the resistance seen by the load. So these are the parameters. There are other parameters, but mostly we are primarily interested in these four parameters: voltage gain, current gain, input and output resistances. Now, how do we proceed to analyze this circuit? Can anyone remember how to proceed? Hello, can you hear me?
Yes, sir.
So how do we proceed? To find the voltage gain. These are the AC quantities, they written in small letters, right? So we write in small letters V naught, the output voltage. This is an AC output voltage, right? AC voltage. Right? Unlike the voltage, we have written VCC, right? Written in capital letter. So that is DC voltage. So these are the conventions. That's how we distinguish between AC and DC quantities. Now these are all AC parameters. The output resistance, that is also an AC parameter, but because that's related to the AC quantity, at the output we are taking the output, the AC voltage, not the DC. So the resistance seen by the the output resistance seen is resistance seen by the AC quantity V naught. So it's not an AC parameter. Unlike the RC, what we have, that is a DC parameter for the DC, or we cannot say AC or DC here, but both AC and DC both are involved here. But here at the output side and at the input side, we have only AC current and AC voltage. So we can also say that Ri and R0 are related to the AC quantities. So how do we proceed? Because these are AC quantities we need to determine. So what we have to do, we have to do AC analysis of the circuit. Right? So in a transistor amplifier, we have both the DC and AC quantities. DC voltages, AC voltages, DC currents, AC currents. And we are analyzing this circuit. We have to analyze this circuit to determine the AC quantities. So we have to do AC analysis, not the DC one. How to do the DC analysis? We have already shown in the last class, designing the biasing circuit. That is, what is our DC, the only that involves DC quantities, and that is how we design or analyze the DC circuit. For DC quantities, the capacitors are open circuit. If you remove these capacitors and make it open, so you'll be left with just this part of the amplifier, that is the biasing circuit, and we have discussed that in the last class. And today we'll show how to analyze this amplifier for the AC quantities. And for AC quantities, the capacitors are short circuit. Right? Capacitors are short circuit because the impedance of the capacitor is given by 1 over omega c xc the reactance, and for AC, for sufficiently high frequency, this becomes quite small, and it's much smaller than the resistances, which are in kilo ohms range. So we assume that they are almost like short circuit. So for AC analysis, first thing what we do that okay, the other thing, okay, we first short circuit the capacitors. We delete this one. Also delete this one. Okay. So now we have removed the capacitors and then make them short circuit. Okay, so we replace the capacitors by short circuit. And next thing we have to do that we remove the DC current and voltage from the circuit. We have this DC voltage, VCC. So we set this voltage to 0, DC voltage. So once you set that DC voltage to 0, now you are left with only AC quantities, right? AC currents and voltages. There are no DC voltage. Now the circuit is ready for AC analysis. So once you set this current, the DC voltage here to 0, so that means 0 volt means ground, right? So it is connected to ground basically when you set the VCC to 0. So we connect these terminals to ground. So before we proceed, we simplify this circuit. We see that RE and is shorted here. This means we have short circuited the capacitors. So RE is shorted out. So what we have to do, we have to remove RE. So we remove RE because it is short circuit. That is one thing. And also here R1 and R2, these two become parallel. They are connected between the two common points. One is this, the base point, the other is the ground. So these two are in parallel. So we remove R1 from here, and you can combine this with R2. Okay. So we have combined R1 with R2, and the emitter is shorted to ground. You can show this like this. And now here at the load end, once we have shorted this capacitor RC and RL, these two are now in parallel. So again here we combine these two into one single resistor. So RL and RC combined into one single resistor. So that is our simplified circuit. Now at the input side, we can do more simplification here. And this part we can replace by its Thevenin's equivalent. So this part of the circuit we replace by Thevenin's equivalent. So when you replace this by Thevenin's equivalent, it will be simply something like this. Let's say this is, we call it Vs prime, and let's call it Rs prime. Right? Where Vs prime will be what is Vs prime? That will be voltage at this point, the base point. So that we're using the voltage divider rule, Vs, and we have R1 in parallel with R2, that divided by Rs plus. So that will be Vs prime, and the resistance Rs prime, that will be the parallel combination of this and Rs. Guys, is this correct? That is our Thevenin's equivalent. Hello?
Yes, sir.
Right. Okay. So I might make mistake now. So now we need to, oh no, not this one. Need the eraser. So I remove this part. Remove this part. Okay. Remove this part. Remove this part. Okay. And so the Rs prime, Vs prime. Okay. So we replace this circuit at the input side, which is Thevenin's equivalent. Now you see the circuit here becomes like this. Very simple, that we introduced in the last class, at the beginning of the last class, while we were explaining the different configurations, right? The difference between the different configurations, main features. So this is our transistor, common emitter is grounded, input is applied to the base, and the output is taken from the collector. So at the input side, we have just a signal source and the resistance, and at the output side, we just have a we just have it can be, we can call it the combination, we can call it our effective load resistance. Uh, uh, so this is our effective load resistance. So RL effective is equal to actually RL in parallel with RC. So this is our effective load resistance. So this is how we can simplify the whole circuit, right, into this simple circuit where we have the transistor and the signal source with the source resistance RS prime and at the load resistance RL. Any question, guys?
No, sir.
No, sir.
Okay. So now this is the common emitter and common emitter amplifier. Now before I proceed to analyze this circuit, I will now show the other two configurations, the common base and common collector, and how we can simplify those circuits. So what is this configuration here?
Common
Hello.
collector, sir.
Common.
Collector. Collector.
So this is common collector configuration. Common collector amplifier. So like before, we assign these currents, input and output currents, then input and output resistances, And then the circuit parameters we need to determine are the voltage gain, the current gain, and the input and the output resistances. So here also you need to do the AC analysis of the circuit. So you set the DC voltage to 0, and that will connect these two terminals to ground, and then make these two capacitors short. So we remove these capacitors. Okay, so circuit is ready to analyze because we don't have DC quantities. We have only AC voltage and currents. But again, we can simplify this circuit. Here the R1 and R2, these two are now parallel. So we can combine these two. So we remove R1. Okay. Also delete this one. And that R1 we combine with R2. So R1 combined with R2. And here you see that the output side RE and RL in parallel. So we can combine these two. So first we need to delete this RE. Okay. And again, like for the common emitter amplifier, you see this part at the input side, we can replace by its Thevenin's equivalent. And once you do that, so we remove this. And so we call it RS prime, VS prime. And this we call it the effective load resistance. Okay. So RL effective. So now this is our simplified common emitter amplifier. And you see that this is exactly the circuit that we introduced in the last class. to show the conceptual common the common collector amplifier circuit. We have this transistor, the collector is grounded. At the input side, you have the input signal with the source resistance Rs, here are Rs prime, and at the output side, you have the load resistance, which is here is RL effective. So this is how the circuit can be reduced to the simplified circuit for the common collector amplifier. Any question, guys?
No, sir.
Okay, so let's move on and we'll now see the common base. So this is our common base amplifier. First, we assign the currents, input and the output currents. And then the resistances, that is our input resistance, and that is our output resistance. Now we follow the same steps to do the AC analysis and determine the different parameters, circuit parameters. We set this voltage to 0. Then these two terminals, they get connected to ground. Then we replace the capacitors by short circuit. So we replace the capacitors by short circuit. When you short circuit the capacitors, now at the input, at the base side, right? So what happens here?
R1 and R2 short circuited.
Right. So they are shorted out. because this terminal goes to ground and that is shorted to this terminal. So they are shorted out, and they become redundant. We just remove this R1 and R2 from the circuit. So let's just do that. So we just remove R1 and R2. Okay. So that is how it's done now. Let's see at the base just grounded, right? Connected to ground. So that's the common base. Now input side is okay. So and this part, the input side, right? We see that we can again apply the Thevenin's theorem here and replace the circuit by its Thevenin's equivalent. So, and let's do that. So then we'll remove RE and then this will look like this. We'll have RS prime, VS prime, and our output side, this load RL and RC will be in parallel, so we can combine this into one single resistor. Right? So that will be our effective load resistance, and that we can call this is okay. So also for common base, we ground the base, and at the input side, at the emitter, where we apply the input for the common base, we have just the signal source with resistance in series, and at the output, which we take from the collector, we have just the load resistance. In this case, RL effective is our load resistance, and that is how it will look like the common base amplifier, the simplified form, and then we can analyze the different parameters. Any question, guys?
No, sir.
Okay. So now we'll analyze these different circuits here. We'll start with the it's too clumsy here, right? So let's get back to our okay. Let's take a fresh sheet. So we start with the common emitter amplifier. How to analyze this common emitter amplifier and see what are the different features we can get for the common emitter amplifier. Common emitter is grounded. Then we have input applied to the base. And we take the output from the collector. So that is how our simplified circuit for the AC analysis looks like for the common emitter amplifier. Then we assign this currents. II is our input current. goes into the input of the amplifier. The I naught is the output current that goes into the load. Then we have here our input resistance Ri, and we have here our output resistance R naught. Any question, guys? Okay, so that is nothing new. Now, what is the next step we have to take? We have simplified the circuit for AC analysis. Now, this is our simplified circuit. We remove the capacitor, short circuit the capacitors, remove the DC currents and voltages. What's the next step? Hello.
Hello, sir.
Yes. What's the
Sir.
next step we take?
Sir, replace the model with an equivalent model. Replace the circuit.
So what are those models?
Pi model, sir. Sir, pi and
There are
T.
two models. We call the hybrid pi and T models. Because the transistor is a device, right? It's a symbol. We need to analyze the circuit to determine the input resistance, output resistance, the voltage, and the current gains. So, in order to determine those parameters, we need to do the analysis, the circuit analysis of the circuit, applying different techniques, right? So, like we have the KCL, KVL, nodal analysis. So different circuit analysis techniques, but cannot apply circuit analysis techniques to the transistor. So we replace the transistor by its equivalent circuit model, where we can apply those circuit analysis techniques. There are two models. One we call the hybrid pi, the other is the T models. These two are equivalent. Now, first I will discuss a little bit about these two models. What are the similarities and dissimilarities? What are the significance of the different circuit parameters that we need to understand in order to develop some expertise on the analysis of the circuits. So what is this model? What do you call this one?
Sir, pi.
Yeah, this is the hybrid pi model. So this terminal, this is our base terminal. This is our collector terminal, and this is our emitter terminal. If you compare this with the transistor itself, this is our transistor. This is our base. This is our collector, and this is our emitter. Now, R pi is the resistance that is between base and emitter. Since this is our base terminal, the current that is flowing here is IB, right? From the base, current is flowing IB. So that's the current here, IB. So in the pi model, basically we are looking from the base side. If you look from the base side, the resistance that you see between base and emitter is R pi. So if you're looking from here into the base, resistance you see is R pi, and that is basically the resistance here, right? Between the internal resistance of the transistor between base and emitter. So that is our R pi, right? So looking into the base. Now here we have the collector side. Collector, we have this current GMVB. So that is the current that is flowing into the collector. So if you come here, the collector we have, and the current that is flowing is IC. We denote by IC. So IC is basically nothing but GMVB. IC GMVB. So the collector current IC depends on the voltage between base and emitter. It depends between the base emitter voltage. So we can, this is our VBE between base and emitter. What is GM? What we call GM? Hmm? Anyone knows what is GM? If you look at the equation GM, we can write like IC by VB, right? The current by voltage. And what is current by voltage?
Sir, conductance.
Conductance. Current by voltage is conductance. And now you see the current here is the collector current, which is the output side, right? Collector output side. And VB is the voltage which is at the input side. So the output current divided by input voltage. So this is called the transconductance, right? Conductance that is transferred from the input to the output side. So that's called transconductance. And the unit for this one, the unit for current is milliampere. In electronic circuits, current are usually in the range of milliampere, sometimes in microampere, mostly in milliampere. So milliampere is taken the standard unit instead of ampere for the current. Voltage are usually in volt. So that is the unit for voltage with the volt. So the unit for the transconductance is given as milliampere per volt. So sometimes students they make the mistakes. They take the current in ampere, also the voltage in volt, and then calculate the this transconductance. But that will give you wrong result at the end. So you have to take the current in milliampere, voltage in volt, and then calculate the transconductance GM, and the unit will be milliampere per volt. Is that clear, guys?
Yes,
Any
sir.
question? Okay. So the other thing here is the R naught. What is R naught? R naught is the resistance that is connected between the collector and the emitter. So what is the significance of this R naught? So if you look into the collector, the resistance that you see is R naught. It's the resistance between emitter and collector, and that is called the R naught. So R naught here is basically the output resistance. It's called the output resistance of the transistor. It's not this R naught. This R naught is the output resistance of this overall amplifier, right? This common emitter amplifier, and this R naught, the small R naught here, is the resistance between the collector and emitter. It's just the resistance of the transistor itself, the transistor device, and this for the whole amplifier. So do not confuse these two. So guys, any question? So that is our hybrid pi model. Let's take a look at the what's now our the T model now. Okay, I have this right. No, that's a mistake. Let's wait. So that is our T model. This is our base terminal. This is our collector terminal, and this is our emitter terminal. Now here the resistance between base and emitter is denoted as RE, and basically this is in the T model we are looking from the emitter side, not from the base side. So if I draw the same transistor here, so looking from the emitter side, look into the emitter, the resistance that we'll see is R. So that's the resistance between emitter and base, and that's the resistance RE emitter, and the current that is flowing here is our emitter current RE. Right? So that is if you are looking from the emitter side, the resistance is RE, and current flowing is IE. So that is what's shown here in the T model. Resistance is RE and current flowing is IE. So if you compare this to the for the pi and T, in the pi model, we are looking from the base side, looking into the base, the resistance is R pi, current flowing is IB. So the voltage here is VBE. And also here, the T model, we are looking from the emitter side, resistance is RE, and the voltage between base and emitter is VBE. So, so that we can write here, the voltage here is same VBE. So the voltage between the base and emitter here is VBE, and also in this case voltage is VBE, right? Because it's between the same base and emitter. And on the collector side we have this current flowing alpha IE. So here the difference between the pi and T model, another difference is that in the pi model the current is shown as the voltage dependent current source, voltage depending on the input voltage VBE, and in the T model it is shown as the current dependent current source, and that current is the emitter current, right? So IC is alpha I. So you see, we know this well-known relations, IC is alpha I, so we have used that here in the pi model. So in the pi model, we look from the base side, and T model we look from the emitter side. And in pi model, the IC is represented by voltage dependent current source, and the T model IC is represented by current dependent current source. Guys, any question?
No, sir.
No question. What is the relation between R pi and RE? Is there any relation? Okay, so what is the relation, right?
So what was the question, sir?
What is the relation between R pi and RE? Any relation? No, can't do that. Guys, is there any relation between R pi and RE?
Sir, R pi is equals to 1 plus beta into RE.
Yeah, how do we get that?
Sir, sir, the voltage between base and emitter VB is equals to, we can write VB is equals to IB into R pi, IB into R pi, and RB into R pi. IB into R pi, which is
No, so I can't do that anymore. That's the problem. Okay, so I'll show you how to, we get that. 3 point,
so the voltage drop will be equal for both
right,
I into RE and
right. So you see that we can write that VBE is from the pi model, it is IBR pi, and from T model it is IE RE, right? So it is IE RE from T model and pi model IBR pi. Now we know that what we can write for IE is IE and IB, what is relation? Relation is beta plus 1 IB. Right? And if you use this relation, if substitute for IE here, then we write that we have IB and then beta plus 1 RE. Right? Now this IB here and IB here will cancel out, and we'll be left with this R pi that is beta plus 1 RE. Right? So there is an important relation we'll see in our subsequent lectures that how useful is this relation. So here we write that we have got that R pi is beta plus 1 RE, or also we can write as this in terms of R pi, that is RE is R pi divided by beta plus 1, right? And these two together, uh, these two together, they are termed as the resistance reflection rule. So that if you have, let's see that the transistor here, and you are looking from the base side, the resistance you see is R pi. If you're looking from the emitter side, resistance is RE. Now this RE is R pi divided by beta plus 1, and this R pi here is RE times beta plus 1. It's called resistance reflection rule because this, if you're looking from the emitter side, the resistance here and the RE depends on the resistance here. So whatever resistance you have in the base, that is reflected into the emitter and gets divided by beta plus 1. And if you're looking from the base side, whatever resistance you have here, that will be reflected into the base and will get multiplied by beta plus 1. So that is a very useful relation to determine the resistance of the transistor at the base side or at the emitter side. If you know the resistance what you have here, so then we will know what is the resistance you will have if you are looking into the base. So just you take this resistance and multiply by beta plus 1. And if you don't know the resistance of looking from the emitter side, so you just take this resistance, whatever you have at the base side, divide that by beta plus 1, and you get the resistance looking into the emitter. So it's easy to remember and very useful relation. Is it understood, guys?
Yes, sir.
Okay. And the different the equations that are used right, to determine this, these are all AC parameters. See that in the heartbeat pi and T model, these are transistor models for and the AC quantities. These are not in DC model parameter models. These are for AC quantities, and these are AC. Also, we call these AC parameters related to AC quantities. And but these parameters, the values of these parameters depend on the DC bias voltage and current. So this is mostly DC bias voltage, DC bias current. So RE is given as the VT divided by IE. So the magnitude of RE will depend on the DC, this current IE, emitter current. Similarly, the I R pi is given by Vt, which is thermal voltage, that divided by the base current IB. The Gm, which is called the transconductance, is given by IC, the collector current, by Vt. So the collector current, you see, has another important role here. Not just we have mentioned one important aspect to of this collector current, that it supports the load current. And the IC should be at least equal to or greater than your load current. That is how you set the IC. And IC also determines the transconductance, right? the value of IC also determines the transfer. So this is, and the transconductance will determine the gain of the amplifier. So the higher is transconductance, the higher will be the gain. So you can also adjust the gain. To adjust the gain, you have to adjust the IC. If you need high gain, then you take high value for IC. So this is the another criteria, right, to select the suitable value for IC. So it will support your load current, and also to set your the gain of the amplifier to a certain value, you have to adjust the value of IC accordingly. So that is another important role the IC plays in designing the amplifier. So other is the output resistance R naught. So that is given by VT divided by, sorry, not VT, VA. So that is given as, that is given as VA by IC. And what is VA, do you know? Any idea? VA is called the early voltage. It's called the early voltage. Early is name of a scientist. It's not early, it's name of scientist who first worked on this phenomena of the transfer, that if you look from the output side, there is a resistance, and that is how we can determine the resistance. So we developed this whole technique to determine this voltage that will that you can use to determine the R naught, the output resistance of the transistor. So it's named after his name. So it's VA by IC. So all these circuit parameters, the emitter resistance, the R pi, the base resistance, and the transconductance, the output resistance, they depend on the one thing, that's the bias current, right? And all this bias current, DC bias current, they are related. IE, IB, IC. So this IC is alpha IE, right? Or IC is beta IB, right? So all these currents are related to basically the IC. So IC actually also determines what will be the values of these different the parameters of the pi and t models. So basically the output, the performance of the amplifier will depend on the DC bias current, right? So that's a very important role the bias current plays into the performance of the amplifier circuit. Any question, guys?
No, sir.
No. Okay,
Sir,
yes.
I missed the part about the voltage VT.
What?
Sir, about the voltage VT.
What voltage VE?
Sir, is it the thermal voltage? Like 0.25 millivolt, this voltage?
VT or which one talking about? Are
Sir,
you talking about this voltage?
yes, sir, yes, sir.
This is thermal voltage. It's given by KT by Q.
Sir, 25 millivolts.
Yeah, our room temperature is about 26 millivolt. Right? But for our sake of simplicity, we take it 25 millivolt, right, for analysis. Exact value, I mean, close to 26. Anyway, so that is our thermal voltage. Huh? Now, I'll show you one more relationship here. We have shown one relation between R pi and RE, and The another relation we have shown that GM is IC by VT, right? And the IC is alpha IE, right? So this one we can write as alpha IE by VT, which we can write as alpha divided by VT by IE. And what is VT by IE?
RE.
Small RE, right? So VT by RE is IE is small RE, so we can write as alpha by RE. And you see that alpha, what is alpha? Alpha is beta divided by beta plus 1. And for large beta, beta much larger than 1, this can be approximated to 1. Right? So alpha is in most cases approximately equal to 1, or it can be approximated to 1. So this we can write as 1 by RE. Right? So GM, the transconductance, also we can write as 1 over RE. So these parameters, the pi model, the parameters RE, R pi, GM, they are all interrelated, right? They're not independent, but it depends on one another because they are all related to collector current IC, right? Somehow. So any question, guys? I think today time is almost up. So I will stop here today.